Hello, my name is Beth Dixon, and this is a video series based on Vicki Borlaug's PowerPoint presentation on the distribution of the sample means for normally distributed data. I wish to thank Mrs. Borlaug for allowing me to use her PowerPoint to make this set of videos. Our example begins with buckets of water. We measure the amount of water in individual buckets and let X be the amount of water in the buckets measured in ounces. We find that X is normally distributed with a mean of 62 ounces and a standard deviation of 5 ounces. If we stop here at just looking at the individual buckets of water, we're limiting ourselves in the power of the central limit theorem. So we will look at samples of buckets of waters. We will take different samples from our population, each of a sample size of 4. In other words, we will take 4 buckets of water, record the ounces in each bucket, and that will create a sample size of 4 in our sample. We will then find the mean and standard deviation for each sample. Here are 5 such samples, each consisting of 4 buckets of water. Notice that we did find the mean and standard deviation for each sample. We're going to look at the means of each of these samples. We do not look at the samples themselves, but at the mean of each sample. We call these, of course, the sample means. If we create a distribution or picture of these samples means, they also will be normally distributed. If the individuals are normally distributed, so are their sample means. We now have our 2 distributions, one for the individual buckets of water and one for the sample means, where we would create an infinite list of sample means. Now we just created 5 here. Now we're going to create 3 more. And that's by answering question number 1. Ms. Borlaug uses the TI-84 calculator to have her students create 3 additional samples. And you can do this and follow along as well. Question 1 states, use the random norm command on the TI-84 calculator to generate 3 more random samples of size n equals 4. Then for each sample, find the mean and standard deviation. This is a class activity that Ms. Borlaug uses, and I suggest that you do stop and pause and do this as well while watching the video. The random norm command is found on a TI-83 or a TI-84 calculator by pressing the Math key, then using the arrow key to go over to the menu, the probability menu, and then choosing random norm. On the newer models of the calculators, you will find an intermediate menu where you will fill in the mu or the mean, the sigma or the standard deviation, and the number of trials or the sample size. For us, that will be 62 for the mu, 5 for the sigma, the standard deviation, and 4 for the number of trials or our sample size. In older models, the random norm command comes up on your home screen, and you will type in 62 for the mean, then a comma, the standard deviation of 5, a comma, and then the number of trials, which is 4, and then close the parentheses. In either case, once you've done that, you will press enter, and that should generate your samples. I hope to put some calculator screens here so you can see what you should get. In either case, you should eventually get your samples. You can then write your samples down and then put them into a list on your calculator and use one variable stat command on your TI-83 or 84 calculator to find the mean and standard deviation. We are not doing these by hand. You can use your calculator and technology to do so. But we will not take the time to do that by hand or generate an example. Every time, if I did have a sample up there, remember, every time you generate one, it will be different and you will not match the screens that I had. But you will generate 3 and get 3 additional sample means and 3 additional sample standard deviations. We are now ready for step 2 in our example. And before we begin, we need to understand our directions. It asks us to find mu, sigma, mu x bar, and sigma x bar, and to fill in the blanks besides the graph. What do these symbols mean? Mu, the first one, is the population mean. Sigma is the population standard deviation. Mu with the little sub x bar is the mean of the sample means. So that if we created an infinite amount of those samples and took the mean or the average of all of the sample means, that would be mu x bar, or the mean of the sample means. Sigma x bar is the standard error of the means, or the standard deviation of the sample means. I'm also assuming at this point that you've had the lecture explaining the standard error of the means and the central limit theorem. This example is more on how it works in problems and how it works with your graphs and your distribution and finding the distribution of the sample means. So at this point, we assume that you've had that and that we're just moving on to the actual application. So let's start. What is the mean? We get that from the stated information, which is the mean is 62 ounces. So mu, or the population mean, is 62. The population standard deviation is given as 5 ounces, and we'll plug 5 in here. We're now ready to find for our, that's for individuals. We're now ready to look at the distribution of our sample means. And by the central limit theorem and the distribution of sample means, we know that the mean of our sample means is equal to the population mean. So that still should be 62. And we know that our standard error of the mean, or the standard deviation of the sample mean, is equal to the standard deviation of the population divided by the square root of n, which would be 5 divided by the square root of 4. It is 4 because our sample sizes are of size 4. That would be 5 divided by the square root of 4. The square root of 4 is 2, so that's 5 divided by 2, which is 2.5. We are now ready for part 3 of our example. Each tick mark represents a standard deviation jump. Fill in the boxes with the appropriate numbers. In other words, what we want to do is to fill in our boxes by counting 3 standard deviations in both directions, positive and negative, for both distributions. The mean is placed in the center, so 62 is placed in the center of both distributions. Now look at the distribution for our individuals. Our standard deviation is 5, so we will jump or count up and then down by 5 each time. Adding 5, our first standard deviation jump, gets us to 67, plus 5 more is 72, plus 5 more is 77. To count down, we will subtract 5. 62 minus 5 gives us 57. Minus 5 gives us 52. Subtracting 5 more gives us 47 and gives us 3 standard deviation jumps in both directions for our distribution for the individuals. We can repeat the process for the distribution of sample means, but remembering that our standard deviation for the sample means is 2.5. So we will take 62 plus 2.5 to get 64.5. Then adding 2.5 again, we get 67. And then adding 2.5 again, we get 69.5. We will subtract 2.5. That will give us 62 minus 2.5, which is 59.5, then 57, then 54.5. Notice the difference in the scales and in the shape, how it will narrow down the shape of our distribution of sample means. Before question number 4, we need to do a quick review of the empirical rule for normally distributed data. In our normally distributed data, we have the mean in the center and 3 standard deviation jumps above and 3 standard deviation jumps below the mean. And by the empirical rule, we know that 68% of the data lie within 1 standard deviation of the mean. Above and below the mean, we go 1 standard deviation jump of the mean, and 68% of the data will lie within that 1 jump of the mean. If we go out 2 jumps of the mean, we know that 95% of the data lie within 2 standard deviations of the mean. 3 standard deviations from the mean is 99.7% of the data, or 99.7% of the data lie within 3 standard deviations of the mean. This is essentially all of the data, but because it goes on infinitely in both directions, theoretically it goes forever to the right and to the left. There is some data that will be outside of this. The empirical rule for normally distributed data thus says 68% of the data lie within 1 standard deviation of the mean, 95% of the data lie within 2 standard deviations of the mean, and 99.7% of the data lie within 3 standard deviations of the mean. Using that, we can now answer question 4A. Use the empirical rule to fill in the following blanks. The middle 68% of the individual values lie between blank and blank ounces. Notice the key words here are individual values. Since we're talking about the individual values, we will use the individual distribution. We will use the numbers here. And since it's 68%, by the empirical rule, that is 1 standard deviation jump to both directions. So that will be 57 and 67, 1 jump in both directions. So the middle 68% of the individual values lie between 57 and 67 ounces. The middle 68% of the sample means, X bar, lie between, well, it's still 1 standard deviation jump, but notice that that will be a tighter jump and be between 59.5 and 64.5 ounces. And since we're talking about the sample means, we will use the distribution for the sample means. Now we will use the empirical rule to find the middle 95%. The middle 95% of the individual values lie between 2 standard deviation jumps, so that lies between 52 and 72 ounces. For the sample means, the middle 95% of the sample means, X bar, lies between, again 2 standard deviation jumps, lie between 57 and 67 ounces. 57 and 67 ounces. For C, use the empirical rule for the 99.7% of the values. The middle 99.7% of the individual or X values lie between, and that would be 3 jumps, so 1, 2, 3, would give us 44 and 77 ounces. For the sample means, 3 jumps gives us 54.5 and 69.5. Here is the worksheet that goes along with this, and you can try this one on your own. I hope to eventually have it posted, or if you're in Mrs. Borlaug's class, it is part of her handouts. Thanks for watching, and I hope this was helpful. Thank you.